I posted some study guide information, so some things about what would be on the final, kind of as an outline of things. And then we have some problems we can talk about and look at today. And the plan for Thursday is to post a few more practice problems of different types and go over some of those. We've covered a lot of material in this class of just different sorts. The final will focus on parts of it. And so the goal is an aim of today is to kind of narrow it down to kind of a realistic expectation of what to focus on. There's not a lot of time between the end of classes and our final, which is on the Saturday. So my intention is to have the final look like the problems that we're doing on homeworks and that we'll study over these next couple of days mostly, and has been on the kind of previous exams for parts of this, so that it's not the whole global picture of things, because there's a lot in there. But homework 11 is looking at some things with the central limit theorem and the law of large numbers. Are there any questions about the homework that you want to ask? Sometimes I find with textbooks that if you read a bunch of different questions, even the ones that are assigned, you see kind of parallels between them. And the first several questions are, what does this thing converge to? And the answer is in all cases it's an average, so it's converging to a mean, and so on. Right? And then the normal calculation. So let's move right along then and look at this description of some things that are on the final. Well, the latest thing that we've done is the limit theorem application, where x bar in large samples should be about normally distributed around a mean and a variance. And the variance is like over n. We'll do one example today where we do some probability calculations based on the mean and variance and x bar being approximately normal. The law of large numbers, this is x bar, x there. So the sample average converges in probability to a mean mu. So just simply stating that or figuring out that works. Not so much asking you to redo the proof or things like that. I wanted to go through that last week because that's an element of probability theory. But the biggest application out of that homework 11 that you might see would be like a normal probability calculation. There. So on the final, just a bit more about that, right? So there'll probably be 6 or 7 questions, right? The previous ones have been about 5 for the hour exams. This one you get the full 2.5 hours. So it might be a little bit longer to cover a little more things, but I'm not going to double the length of the exam. Right? So some of you will finish earlier, and that's fine, but you get the full 2.5 hours to work on it. Right? So you can have 2 pages of notes. You can write on both sides. So that you can write down formulas for densities. You can write down examples of computing problems, notes, text, whatever you want to put on there. You can use your sheets from the previous times, get them onto 2 pages, or completely rewrite it as you see fit. Right? Calculators, it double checks that your calculators are working. This will be a few numerical things on there. Right? So central limit theorem primarily. Univariate transformations that we did in chapter 7. We did things with PDFs. So if x is the density, and we want the density for y, and we have some transformation, we have this PDF method of going about that. So the other way we did that was with a cumulative distribution function. So this was, just ignore that part there. So we want the cumulative distribution function of y. That is, if we plug in the g of x and then we take the inverse, it's either increasing or decreasing depending on what x is, what's happening with x, with the g function. We do that, and then if you wanted to get it to the PDFs, we could differentiate this thing of y to get back to the marginal density, to the density of y from the cumulative. So I'm doing a transformation in one way or the other, like we've seen from chapter 7 and those homeworks. One thing that was put on that homework was things from simulating a distribution. This is much the same case that for a uniform, so if u is uniform and we let u equal the cumulative distribution for something, and then solve for that one, solve for x, then the x value, we generate a u, do that numerical transformation and get x, then it has that cumulative distribution function. So we use that in the simulation. So that might be an example of something, a transformation. We use moment generating functions. There are a couple ways that I move this. This is going to not stay on there exactly. Right? So as we moment generating functions, we use a couple ways. We have a linear transformation of a random variable, right? And the moment generating function becomes this thing. And so if you x is a distribution you know and recognize as moment generating function, sometimes the linear transformation stays within a distribution family, so you can recognize what it is. Right? If you add together 2 independent random variables, and the moment generating functions multiply, and so when you're adding together gammas or Poissons or things like that, they became the next version of that, another version of that same distribution with the parameters changed. So we could figure out what the distributions were from that. Right? And so this actually shows up a bunch of places in the book, if it does it for discrete distributions, for one aspect of it, and then continuous, and then sums, and so on. So we did some of that. In chapter 6, when we looked at multivariate distributions, we're going to restrict it in this exam to the continuous ones. Right, so we're not going to do the 2-way tables of counts and things like that. Or we're not going to do multinomial. We talked about multinomial in other contexts. So we're just going to do the continuous ones where we get a joint density function. I've got a joint density function of 2 random variables, right? An f of xy function. We might want to get the marginal by integrating out one of the distributions, integrating out one of the variables. We might want a conditional density, f of y given x, then is the joint density over the marginal. Right? This says here ranges of support do matter. So I don't plan to do anything too tricky or hard with the range in terms of, but if it's a positive random variable, you integrate from 0 up to infinity. If it's beta, you do between 0 and 1. And if x or y has some restriction, you probably want to mention that there is this range of restriction where the density is positive in that. So paying attention to, it's not planned to be a terribly difficult one, but part of the complete answer is mentioning where is that variable located. That was one thing in chapter 6 using the multivariate. We also did conditional expectations. You know that I like these conditional expectation things. And the conditional variance, we'll look at a problem today that uses that. So it's a useful way of thinking about where variability is. Variability in x, and then there's variability in y given x, and you can put these two things together to get means and variances, and sometimes distributions. I don't plan to ask a particular Bayes question with these continuous ones. Right? Just taking the ratio of these things to get a conditional is as much as we'll do. Or effectively, you're doing something with Bayes. If you start with the joint distribution, you take, well, in any case, the joint, and we get a marginal, take this ratio as a conditional. We'll kind of follow that pattern for those. Going back a little bit further, we did a few things with continuous distributions. If I just give you an f of x function, right, and you want to find the mean, we just take the expectation of x like that, an integral of x times its density, or x squared, or the variance. This general variance formula, the variance can be written as the expectation of x squared minus the expectation of x quantity squared. This is very useful. We've applied it a number of times. So, and then the cumulative distribution, the probability that x is less than or equal to some value, the cumulative distribution of x, and this was an integral that's set up there. So, with the transformations, right? We could do some trace of transformations with the CDFs. We could also just use that to calculate probabilities and areas. In terms of the continuous distributions we've looked at, the plan, you can write down as much as you want about the different distributions, about finding their means or integrating them or things like that. But the plan is, I'll remind you, on the form of the PDF or CDF or mean or variance or moment generating function. So, that as needed. So we can ask about that. It'll give you some background information about that. We might transform one of those. We might compute probabilities based on one of those. Right? So if you have the CDF of one of these things, and it's like the exponentials, a form that you can write down. Right? You can find the probability you're less than a value, or you can find percentiles. So using some of those formulas a little bit. For the normal distribution, some of the things with normal distribution are, we use MGFs, moment generating function, for some of that stuff. To transform a normal, like take the log of it, or take the x, square it. We did some of the transformations right, that way. But beyond that, being able to use the normal table to look up a probability. Right? And on the back of the other handout is the copy of the normal table, and we'll use that one. So that'll be provided. You don't have to bring that table to the exam or copy it for you as part of your notes. But that's the one we'll use. So it's been a while since we actually looked at the table and did something with it. So that's the one we're going to use. And if you can calculate areas, that would be good. Right? The last two things, we did a lot of discrete distributions, and they have an important role in applying statistics and things. We'll primarily look at the binomial. And we'll do a binomial example today. So we calculated some binomial probabilities. We had the mean or variance of these things. There's some assumptions underlying that binomial. Right, that independent trials, constant probability, number of successes out of a certain number of trials. It also had a kind of a central limit theorem approximation, right? So if it has a mean and a variance, particularly of p hat, then the central limit theorem says the distribution of p hat as that sample size gets big is approximately normal. So you get a mean and a variance, maybe you get a normal calculation out of that. But there was others, geometric. We won't put those on there. You can focus on that one discrete and its formula and its properties. Right? The other thing that I'm generally a fan of is these kind of conditional probability trees and Bayes theorem in that form. Right? So if you had a probability of some event A and the probability of event B given A or not A, right, that was what gave us this little tree. This is going all the way back to chapter 3 or part of it. And you can get the opposites of any of these probabilities. And you can calculate the probability that B happens by adding up the probability you get to these two endpoints where B is. And you can reverse the probability, which technically is Bayes' theorem, that the probability of A given B for these discrete events is the probability, say A given B, well, is the probability you have both of them, which means that you go the probability down this branch divided by the sum of the two branches where B happens. So that's the formula there. So that's a lot of material. We're not going to have questions that use every part of this. And some of these things overlap, right? So some of the normal probability calculations could be as part of something. You could have one of these distributions and then do a transformation of it. And so, but that's kind of the biggest range of things that will be on it. And so some things are definitely excluded. So any questions? Yeah.
I'm sorry, I don't know if you covered this for the multivariate transformations, but do we need to know the Jacobian?
No, you won't need to know that transformation. It'll all be univariate for doing the PDF or CDF methods. Yep. All right, so let's look at some questions. And so some of the problems that I came up to look at today to illustrate those are summarized on the handout there. Right? So you could, for instance, be given something that's a gamma distribution and say we're going to transform it and take 1 over the variable. And so the question might be simply, what's the PDF of that new variable? So we have that x is gamma, random variable. Then x is going to be measured as greater than 0, and the density. And I would give you this density formula. It's 1 over gamma alpha, beta to the alpha, x to the alpha minus 1, e to the next x over beta. So you'd be given that, and then told that y is a transformation where we take 1 over that variable. And what's the probability density of y? Next on that one. Right, so this is a variable where the CDF is harder to use. So we would do the way we go about this. We take the transformation, x equals 1 over y. We take the derivative of that. We take the derivative of that thing, so it's negative 1 over y squared. We take the absolute value of that thing, which is 1 over y squared. We don't have any negative densities. And then, so the density at y is the density of x, evaluated at the transformation at 1 over y. X is there. And then we multiply on the adjustment. the next task is to plug 1 over y into all the values of x. So the multipliers out front are the same. And then we have a 1 over y, alpha minus 1. And then these negative is 1 over y, so it's y over beta. And y is positive. X is positive, 1 over x is still positive. And you can simplify this. Oop, I need to get the 1 over y squared in there, sorry. That still is multiplied in there. Right, so you could group those, the 1 over y's together. Gamma alpha, beta the alpha is 1 over y, and this becomes alpha plus 1. So we add the 2 into there, e to the negative 1 over y beta. So that would be the density. That would just be the answer to report. This thing happens to be called a inverse gamma random variable. It's related to variances. But anyway, that's the procedure. If you started with this inverse gamma 1, right, we could say, well, instead of starting there, we could go the other way. What if x is 1 over y? I kind of restart the whole thing. Right, then the inverse is, the inverse, take the derivative of this thing. So it's negative 1 over x squared. It's the same process. And the absolute value of that derivative is 1 over x squared. So going the other way, going backwards, the density of x relates to the density of y. And what do we put in there? We put in the transformed values going the other way, 1 over x. And then we have to have this adjustment of 1 over x squared in there. So as we, right, so if we're starting with this is y density. Now we're putting 1 over x where there's a y. Then it comes out to the 1 over gamma alpha, beta the alpha is still there. Well, 1 over x is just x. And 1 over y, well, if you plug in 1 over x with that, 1 over 1 of it is the x over beta. It goes back to what it was. And there's this 1 over x squared. You can't forget that bit, right? So going back to the other way, then if you group the x terms, then we're back to our density 1 over gamma alpha, beta to the alpha. There's an x to the alpha minus 1. You subtract the 2 there. And so we've gone from started with a gamma, we went to an inverse gamma, and then we took the inverse of that, and it came back, and it was gamma, which is not surprising at all. But that's just kind of two illustrations of the process. But any so a second, what they're listed as part C. Let's say y is cx plus c0. So c0 is kind of a fixed cost. C is a cost per value of x. Right? The moment generating function of x for a gamma is 1 minus beta t to the negative alpha. So what is the moment generating function of y? So how did the formula? The moment generating function of e to doesn't involve x. So that just can come out as a multiplier. And you get expectation of e to the c x t, or maybe you do e to the c0 t, expectation of e to the x, and then kind of a ct over here. So different ways to do it. But the general formula was we're going to do the moment generating function of x evaluated at c2. This was a, if you multiply by something, the multiplication ends up there. That's a formula you could write down and have. So when we plug in ct in place of t, right, there's just going to be an extra multiplier. C is going to show up in there. So this thing is e to the c0t, 1 minus beta c t to the negative alpha. That's the moment generating function. Except for that e to the c0t, except for that constant shift, it looks like another gamma. So x was greater than 0. Y now is shifted over. It's this constant, so it's shifted over. Other than that, it looks like a gamma. What's the mean of y?
First moment evaluated at 0.
You can take the first moment evaluated at 0, right? We'll get it for you. If you have this linear one, you could go straight to that. So there's two distinct ways to go. Right? The expectation of y is the expectation of cx plus c0. So it's a linear transformation. It's just the expectation of x goes in there. And for our gammas, it's alpha plus beta plus this constant. And so if you take the first derivative of this, right, moment generating function of y, and then evaluate it at 0, you should get that thing back. So this is the quick way with linear. This is the moment generating function way, and it should get you the same thing. You'd only need to do it really one way, but taking the derivative of this thing, well, we have to use chain rule, right? Because there's two parts. E to the c0t times the derivative of the first one, or the second part, sorry. Negative alpha 1 minus beta t, beta c t, times the negative alpha, times the derivative of this stuff inside, so this negative beta c. That's the first part. As the first part times the derivative of the second, now we'll do the second part and the derivative of the first. Give alpha, sorry, minus 1. I forgot the minus 1 there. So the derivative of this one, where we get the e to the c0t back, and then the c sub 0 shows up there. I don't know if the actual application on an exam would be as complicated, but the putting in t equals 0 into this, e to the 0 is 1. There's a negative and negative, so those constants, alpha, beta, c is there. And if t is 0, this whole thing is just 1. So that first part just goes down to that. And when t is 0, e to the 0 is 1. 1 minus 0 is 1. And it's just 0. So it's the same thing. But we use moment generating functions to get things like that. But the, you know, the getting a new moment generating function from a transformation gives you something like that. If x1, if you had two variables, say x1 is gamma alpha 1 beta, and x2 is another gamma alpha 2 beta, take y, and they're independent. Y equals x1 plus x2. What's the distribution of y? So this is the other moment generating function one, right? So the moment generating function of y would be the moment generating function of the first one times the moment generating function of the second one. Because they're independent and we're doing this special sum. So if it's 1 minus beta t to the negative alpha 1 and 1 minus beta t to the negative alpha 2. And again, I would give you the, somewhere in the statement of the problem, this is the moment generating function of a gamma random variable. And then you just have to use these results. And so when they come together, 1 minus beta t, negative alpha 1 plus alpha 2, and that again looks like a gamma random variable. So that's a bit like that. But any questions? Right, so let's look at a normal calculation problem. It's been a little while. Well, we could do some with the simple limit theorem, but so let's say for a problem that x has a normal distribution with centered at 100 and a variance of 100, or a standard deviation of 10 squared. And then y given x has a normal distribution centered at 2 times x and a variance that is 5 squared. This is actually would be an example of kind of what you might see in a linear regression, where there's a distribution of x values, and then there's some relationship between y and x. That this 2x is this is the 2x line there, and the y values are some scattered randomly about that line. You might have y values, you have a bunch of x's down here that are kind of normal. 100, kind of here in the middle. Right? You have some spread of the y's. So what's the expected value of y? What's our average outcome? Expectation 1, so the expectation of y given x is 2 times x. So this is 2 times the expectation of x. And the expectation of x was 100, so that's 200. So y on average is going to be 200. What's the variance of y? Well, it's the other formula. Expectation of conditional variances plus variance of conditional expectation. And this model, the variance of y given x is just constant. 5 squared. No matter what x is, kind of equal variance of the y's vertically. And then the variance of expectation of y given x is 2x. So 25 is just a constant. And then this thing, you bring the 2 out. Right? Things inside of big multipliers and variances get squared. The variance of x is 100. So this is 25 plus 400. And with 425, and that's a variance. What if, so one concern in linear regression is that the variances are not constant, right? But actually variance is spreading out or changing as you get bigger, right? Things are getting bigger, their means are going up, but also the spread of the variability is happening. It happens in a lot of different applications. So let's redo this one, but it'd be nice to have it on the same page, but I think for space we're going to put it over here. So same mean for x, x isn't going to change. But now the conditional distribution of y, same slope, but now this is going to be 0.0025 x squared. So the standard deviation of y given x, the square root of that thing would be 0.05 times x. So the standard deviation is spreading as you go up. In terms of relationship to data, you have the same 2x line go here, but the data is kind of spreading out away from the line as those get bigger. So what's the expectation of y? Well, the expectation of y is still the same thing. That doesn't change. It's the expectation of 2x, and the expectation of x was 100, so that's still 200. Still the same average. But what's the variance of y? The expectation of conditional variance plus the variance of the conditional expectation. Now the variance of y given x is 0.0025 x squared plus the variance of 2x over here. So this thing, 0.0025, can come out, expectation of x squared, plus 4 times the variance of x. What's the expectation of x squared? That was the thing where the variance of x can be written as the expectation of x squared minus its mean squared. So the expectation of x squared is variance plus expectation of x quantity squared. So the variance of x was 100. The expectation of x is 100. That gets squared. So this thing is 10,100. So these things together, so 0.0025 times 10,100 plus 4 times 100. This ends up being 425. How much is it? 0.25. Just a little bit more. I kind of chose that 0.0025 to make them almost the same. But this, it's going to be just a little bit more. So that's these conditional formulas, right? That's just the way it works out. question, so it was the same conditional variance formula. We just ended up with a little extra piece to do because the variance ended up being a function x squared ended up being there instead of a constant. So, normal calculation. So y given x is normal 2x 5 squared. On the other one, y given x is normal 2x and then 0.0025 x squared. What if x equals 90? We have a specific value of x. Well, this is normal, the mean of 180, and a variance of 5 squared. This one, the average is the same, right? But if it's a little bit less, it is 0.0025 times 90 squared, which is a little bit less than 5 squared. So they're slightly different distributions. What's the probability that y, given that x equals 90, what is the probability that y is greater than 185? We're just going to write it for convenience. There's a chance that it's greater than 185. So to do a normal calculation and use that normal table, we have to standardize it, right? Z-score it. So we're going to calculate the probability that we're going to take our 185 minus our mean and divide by the standard deviation. And that's a standard normal. So this one, probability that Z is a standard normal is greater than 1. So to finish that, I mean, you get a lot of the credit for setting things up, showing the Z-score. We have this table. So look at your table. What's the chance that you're greater than 1? So looking at the table, I'm going to get a value of 1 here. And the probability. But what does that probability represent? Is that the answer? 8413. Right, so these things are all positive, and it's a, oh well. Right, here's, if that's our value of 1, it says this entire area is 0.8413. So what's the chance we're bigger than that? 1 minus that, right? Just getting the other side. So this side is 1 minus 8413, 0.1587. So with normals, area under a curve, often had to do 1 minus. So the answer to this thing is 1 minus the probability that Z is less or equal to 1. So 1 minus the 0.8413, so 1587. How about this one? Right? So this one, the probability that y is greater than 185. Right? When we Z-score this one, 185 minus 180. Now we divide by its standard deviation, right, which is smaller. So the square root of that is 0.05 times 90. That would be 4.5. Right? So probability that a z is greater than 1.11. If it's average of 180, but a smaller standard deviation, the value is likely to be closer to there, right? So the chance that you're bigger than some outlying value goes down. And so if we look up, what probability am I going to use for this one?
0.8665.
8665. So if we go down here to 1.11, that's that neat, I think my little circle thing there. 1.11, 8665. Make it bigger. Well, you can see it there. So 1.11, 8665. Has an area. Yeah, the circle's off, it didn't adjust. So 1 minus the 0.8665 or 0.135. So they have the same mean, so the one that has smaller standard deviation has a smaller probability of being really big. Yep.
How are you figuring out where to look on the table? I don't really understand.
Yeah. So we had, the original question was phrased in terms of 185. And so to get back to the standard normal with mean 0, variance 1, we subtracted the mean divided by standard deviation. And that was a z value of 1.11. Right. So we're looking up our table calls it x, but we're looking at that 1.11, and then the area is listed, next to that. So on the table, so we're looking at these x values, right, down here, going down these until we get to the 1.11. And then the area associated with 1.11 is listed there as the 0.8665. And so in terms of a picture of the normal, here was 180 on our average, and we want the chance that we're bigger than 185. That was on the original scale. And when we change it, standardize it to a 0, 1, in the second case, this became 1.11. So when we look up 1.11, it gives us the area to the left, either under a corresponding standard normal or this one with the mean and variance that we're using, so 0.8665. So then the opposite area, right, is 1 minus that. 0.1335 to get that area. But it's taking the value, subtracting the mean, dividing by the standard deviation, which gives the z-score, and then looking up the table value here, and then deciding, do we want this one, or do we want 1 minus that, or something like that. With any other? What happens? So let's say we have some random variable, say y has mean 180 and a standard deviation of 4.5, and we take n equals 10, or let's make it easier on ourselves, n equals 9 independent samples. And what we're going to do is take the average of those. And we can suppose that y is pretty close to normal. Maybe not perfect, but pretty close to normal. Or maybe even it is normal, but it's pretty close to normal. What's the probability that y bar is greater than or equal to 185? Over here, the probability that y was greater than 185, or 0.1335, because it was the z value greater than 1.11. So that works out there. What happens when we take the average? calculation. We don't just do sigma anymore. Sigma mu. We'll do sigma over square root of n. So for y bar, we're going to use normal with the mean of 180. And now the standard deviation is going to be sigma over the square root of n, or 4.5 over the square root of 9, which is going to be 1.5. So it's narrower because of the average. So for this one, I have the probability that it's greater than that. It's probably going to be the probability that a standard normal, subtract 180, now divide by 1.5, and this is probability that a standard normal is greater than, so 5 is 3 and a third, right? 3.33. So, yes.
On the exam, would you tell us to assume that it's like basically normal?
Something like that, or close to normal, so that either the central, if it's not normal, this could be close to normal made by the central limit term. Now 9 is a pretty small sample, but if y started with normal or very close, then y bar is going to even be more normally distributed, that you're unlikely to get all values of y that are really extreme, and it's kind of going to dampen out some of the skewness. Right? If I said, y is a little bit skewed, and I use something like, 60 or 90 or something, then the distribution of y bar is much more normal. Okay. So I think that this is right. So 3 times this is 4.5, and 0.5 over that is a third, right? So what's the chance that a standard normal is greater than 3.33? Right under the table. We got to look a little bit smaller so we can see the numbers. We're looking at these x values. We're going out here to 3.33, so it's in the last column, and 3.33 is down there. Oh, it's in the very last column, right? So yeah, here's 3.33. Not much probability that you're beyond 3 standard deviations, or 3 1/3. So 0.9996 if you're less than that, so 1 minus that you're bigger. So this is 1 minus 0.9996 or 0.0004. Not much probability that an average of 9 is beyond that. But any questions on the normal tables? So there's 3 other problems listed there. We can set them up, and then if there's questions, we can go through more, calculations and things. The third one there is a conditional probability. So you have some company, say your city is buying bricks to pave some sidewalks and make it all nice with bricks and things like that. And they're getting so many that they're going to contract to a couple of different companies. And 40% of the bricks are going to come from company 2. That implies there's only 2 companies. That company 1 is going to be 60%. Maybe this is probability of A and probability of the opposite of A. Now some of the bricks come in and they're chipped or broken or just generally defective. Let's say that the probability that something is defective, one of these is defective in company 1, I'll put company 2 up here because that's the order I put it in. I don't know why I switched the order. I did 2 before 1, but I just did, right? And then company one has a 3% defect. What percent of all the bricks are defective? In symbols, maybe you would call this D given A, or not A. This one is D given A, defective among the company. First company is company A, the other one's the opposite. So in answering these, you can make a tree. You can say here's company one or company two. Company one has 60% of the business, and this one has 40%. Each one of these, the product is either defective or not. D bar means not defective. You can use traditional A and Bs. You can use different notation for opposites. You can do it all in words. Whatever is fine. Defective. Company one is 3%, and for this one, 6%. So the probability of defective is 60% of the bricks come here, 3% of them are defective, and then 40% are company two, and 6% of them are defective. So that's 0.018 plus 0.024, 0.042. So about 4.2% of the bricks would be defective. Right? So if they really need 10,000 bricks, they could figure, well, we better order in an excess of 4.2%, or maybe a little bit more, just to be on the safe side, to have enough to finish the project and not have to reorder. So let's say that some bricks have been delivered, and you sample the bricks, and you're not sure which company has come from because they've all been stacked together, but it's a defective one. Right? What's the probability that it's company one? We're multiplying these out to 0.018, multiply these out to 0.024. And so our conditional probability of one thing given the other, you can take the probability of both things over the probability of the thing you're conditioning on. So 1 and D over the probability of D. And the Bayes theorem type thing for the both of things, the probability of company one, that's the probability of defective among company one over the probability of defective. So defective and company one is 1.8%. Defective overall is 0.042. And these things all divide by 6 conveniently, so it's 3/7. Initially, the probability of company one was 3/5, without knowing it. Right? 3/5 of the business are coming from that. But now it's defective. What percent of the defective business comes from company one? Only 3/7. It's a smaller amount. Right? Company one is less likely to be defective, so defective bricks are less likely to come from them, and the probabilities change. So that style of thing could be a question. Any questions about the tree? What's the chance it's not defective? If it's not defective, what's the chance it's company two or company one? So you can mix and match different things like that. Kind of related to this context, let's say X is the number of defectives that we're going to have. Bricks. Broken, cracked, scarred, ugly bricks. Let's say that you sample n equals 20 of them, and the probability of defective 5% effective, right? And we pick 20. If that's the probability and they're independent and we're picking that fixed number, right? Then X has a binomial distribution with 20 and P 0.05. What's the probability that you get at least 3 effective out of your 20?
Back to that exam one note sheet real quick.
Oh, yeah. Something, right, so at least 3 defective. The first step is, right, you don't want to calculate 3, 4, 5 all the way to 20. You want to take 1 minus less. 1 minus the probability of less than 3. Less than 3 is going to be 0, 1, or 2. The probability of 0 defective you can either do that with the binomial probability formula, or just 0, 1 is a little more intuitive, that there's a 95% chance that one of them is not defective, and you have 20. So it has to be 2 to the 20. What's the chance of 1 defective? Part of the answer, right, is you have to have 19 that are defective, and then 1 that is good, or 19 that are okay and 1 that's defective. The combinatorics is there's 20 ways to, 20 bricks, you gotta choose one of them. Right? There's a 20, choose one out here. 20, choose one, it's just 20. Add the probability of 2 defective. Is 20 choose 2, it's 0.95 to the 18th, 0.05 squared. Right. And our 20 choose 2, you can calculate as 20 times 19 over 2 times 1. So that's 190. So you calculated those 3 things and added them up. That's the chance of 0, 1, or 2, and 1 minus, that would give the probability that it's asking for. So let's say you pick 200 bricks, for example, 200. What's the chance that you have fewer than 8 defectives? So n is 200, p equals 0.05. What's the probability that x is less than 8? So you could do, let's make it 2,000 bricks. What's the chance that they have less than 80 defective? Right? You don't want to do this as binomial.
I can have R do it for me.
Huh?
I can have R do it for me.
You can have R do it, yeah, you can have your R. I'm not sure, I'm surprised it's not installable on phones, right? You can just do it on here. But if X is binomial, the expectation of X is n times P. And the variance of X is n times P times 1 minus P. And moreover, P hat X over n, the expected value of the sample proportion is the actual rate, P. And the variance of P hat is P times 1 minus P over n. Right? And the limit theorem applies. P hat is like an average. add 0 or 1 every time you get a success or failure and divide by n. That's the average. p-hat is a sample average. Okay? So this is the probability. Well, there's no approximation here. Just dividing by n, 80 over 2,000 is the probability that p-hat 8 over 200 is like 4 over 100. So the chance that the p-hat is less than 4%. If the rate is really 5%, what's the chance we would observe less than or equal to 4%? So central limit theorem would say that p-hat is approximately normal, or the way we use it, centered at 5%. And its variance 0.05, 0.95 over 2,000. So if we have a normal distribution in that question, we can z-score it and then look it up on the normal table. So this is about approximately the probability that z is less than or equal to, so we're interested in 0.04. We subtract and then divide by the standard deviation, which is the square root of that whole thing. I don't know what that comes out to be exactly. Let's see. That kind of small. Where's that one? Okay, we can see it. Let's see over here. Right, so we want the z-score is 0.04 minus 0.05 divided by the square root of 0.05 times 0.95 over 2,000, negative 2.05. So it's negative, right? So the z-score thing is the probability that z is less than negative 2.05. So we're going to go to our z table and look up 2.05. And 2.05 gives us 979. We don't have negatives. We got to look up the positive, the absolute value. So we have a normal here, and here's 0, here's the z value, and the numbers, and 2.05, right? If we look it up, sorry, going in the wrong direction. 2.05. When we look up that number, it gives us, what was the area? 9798. So 0.9798 is the area. So the opposite is 0.0202. And because of the symmetry around 0, that if we had negative 2.05, we flip it all around, we're going to have the area less than that be 0202, at 2%. And so that's the answer, 0202. About 2% of the time we would get, out of 2,000 bricks, we would get less than 80. So I might, kind of how I'm working some of these things. I kind of start with one type of thing and then ask kind of a related question. Kind of some of these distributions things kind of come close together. And so, I'm not going to ask independent questions about all the different pieces, but a couple might blend together. Keep it 6 or 7 questions. But so how good is this approximation? And then we can talk about the last problem that's there. So the probability for a binomial that you're less than or equal to 80, when you had 2,000 as the sample and the rate was 0.05, is 0.020, that's what it is, right? And the probability for a normal that you're less than are negative 2.051957 is pretty close to it. To do the normal, yeah, anyway. So that comes out pretty, those two probabilities, the normal probability or the actual binomial, that's kind of, reassuring that it's pretty close in that case. Last study question, any other, was one example, that's stuff on the final. The last stated question here is one of these that does a joint distribution. So find the value of k. Well, this thing has to integrate to 1, so you have to integrate over both dimensions. And then if you have, find f of x, maybe find f of y, integrate over 1 dimension, take the ratio. So that type of question is if I didn't make you find that thing, that the constant k is actually 3 over 28, x plus y squared. That's the density when x is between 0 and 2, and y is between 0 and 2. If the ranges of x and y change, right, then this constant has to change to make the whole thing integrate to 1. Well, what's the marginal distribution of x? X and y are going together. Are x and y independent of one another? Can you factor that into an x thing times a y thing? That doesn't factor. So x and y are not independent. There'd be some I won't ask you about covariance and correlation. I won't ask you to compute that. I didn't mention that before, but. But if you wanted to get the marginal for one of these things, right, you got to integrate out over the joint density, integrate y. So y goes from 0 to 2. So 3 out of 28. And with y, and that's x, y, and this is y cubed over 3. And then this is y going from 0 to 2. And so 3 out of 28, you put y at 2 in there, you get 2x. And this thing ends up being 8/3. Right? So if you multiply through by 3 at least, you divide by 2. Right? So there'll be a 14 out front. So divide by 2, this will be about 3x. And then multiply by 3, divide by 2 equals 4. And x is in that. That's just the mechanics of doing the integral. But any questions? I'm just taking my notes. What's the conditional distribution of y given x? So y is the random variable, and you get some fixed value of x, you know x. The joint density of these two things over the marginal density of x. So just take the ratio. It'll give you something. So the joint density was 3 over 28 x plus y squared. And this marginal, I'm not going to use the final version. I'm going to do this version. I'll put the final one here. You try to gauge where it's gonna be easier to work with, to simplify. Right. So this becomes 3/2. That 14 goes on top, and 14. Right. X plus y squared over 3x plus 4. That, you multiply through or something, but that ends up being the conditional density. If y is a particular value, you might compare these things, y equals, 1 versus, y equals, 3/2 or something. If you looked at it at 3 different points, you would get different distributions, densities for x. That might be interesting to see. But so if you've got this, plug in, say, y equals 1, the density of y given x, when y, okay, yeah, sorry, y given x. No, I'm sorry, this is given x, I should say this, right? But really you want to put an x here. Right, x equals something, or x equals something, right? So conditional on x. You can pick some number to stick in there. So let's say x equals 1. And the conditional density of y is when x equals 1. Well, you're going to plug 1 in there, so you get 3/2 times 1 plus y squared over 7. So 3 out of 14 times 1 plus y squared. And y goes to 2. As an example. The latter parts of the stated problem, imagine, well, what if you did that, and then wanted to transfer them, like multiply them by 5, or take an e of that power for one of those. So then that would be one of those PDF transformation things. Right? Well, so those are some illustrations of problems, right? Some review things like probability trees, binomial, normal calculations are a little bit older, so we did those. Right? And what we'll do on Thursday is I'll pull together some other problems from last year's exam and study problems and put those together. And we can go through some of those and also answer questions, right? If you look through the stuff that's on the final and say, wow, I don't know what exactly you're going to ask about that, or that's a hard topic, let me know, and we can try to do a problem related to that. The final thing, just evaluations are out there, right? So I sent an announcement reminder. So please do the evaluations. This course will be taught next spring, either by me or another person, and your comments about it was useful, it was understandable, if the math looks good, what do you think of it? Did you learn things from it? Suggestions would be much appreciated.
I think that it's really important. They don't want to feel like they're great at it.
I have a meeting, I can finish right after this, so
So for the final project,
yeah.
are we doing the one where it's like 3 problems? Does it just do any 3 problems that we did last?
Yeah, something kind of connected to some topic would be great.
So like trying, because the way I did it last night, because I did all the problems last night, I didn't write anything later. I chose one chapter that I struggled with, and I just did that.
Oh,
That
okay.
I do it for.
Yeah, that's fine. Yeah, and so kind of provide some context, with that area, comment on what's, was there a conceptual, kind of process thing that was challenging? What did you learn by reading? That'd be great.
All right.
Yeah.
All right, thanks.
Oh.
We have a question about part of our project
Yes.
that we wanted to show you.
Yeah.
There's a website that we found, so we're doing it based on March Madness.
Okay.
And we found a website that gave each team probabilities based on their
Uh-huh.
seed of moving forward.
Right.
But we were having trouble computing like the conditional probability because we wanted to see like what's the chance that this team wins this game based on who they actually played.
Yeah.
So we couldn't get the probabilities to work out.
So, so if at each, initially they have kind of their seed probability?
Yeah,
Yeah.
so they did a seed probability that they'd make it all the way, and then we can show you the website, but it kind of showed the probabilities that each team would make it through based on each game.
Mhm.
So we kind of wanted
So
to
kind
break
of
it down.
evolving.
Yeah, yeah,
Right.
So we didn't know what to do because the tree seemed to be backwards.
yeah.
In
Because
a way.
we always broke it down so that the tree got bigger, but this is the tree getting smaller as they're playing each other.
Yeah, so if you take it from perspective of one team,
Mhm.
they either win or lose.
Yeah.
Right. And then the next, if they lost, they're done.
Yeah.
But if they win, then they either win or lose. So it's kind of an asymmetric
Yeah.
tree
I just
growing
didn't know
out.
how
And,
to do that because it depends on the probability of the other teams.
Yeah, so you could do it for a few steps in a way, right? So, you know, if they have, if your team's here and win or loss, and there's some kind of probability, you know, a first probability that they win this one, you know, versus this, you know, then you have to see what's the chance that they would win this game or lose, right? And it depends on who they're playing.
Yeah.
right?
Yeah.
So in the brackets, right, it's really, the brackets are really kind of going like this.
Mhm.
So the probability they win the second game would depend on the probability they win the second, assuming that they've won the first.
So should we try and build the tree, like if we try to compute this out, try and build the tree like the way we know how instead of making it go smaller, try and build it up like the way you're describing there?
So you could try to, you know, it becomes, there's a certain probability that they're going to face.
Mhm.
So at the second level, there's two possibilities, right? Two teams they might face. And so you could calculate for those two teams the probability you get opponent A or opponent B, right? And then there's a probability they win given that it's that opponent, right? So it's kind of taking a couple steps to get the next level probabilities and so on. So maybe going through that for a few,
For a couple teams?
couple
Okay.
teams, yeah, a couple depths in there.
Instead of, okay.
I was trying to find the website because it was like some of the, it was just like, or some of the probabilities just seemed, what was it?
It was right now, because I was one of the ones that I cited, so go down, go down.
This one?
Predictions, I think that.
Uh-huh.
And like,
Well, okay.
yeah, so it gave, yeah, so we were trying to do like, what's the probability that
Probably
Virginia
win
wins
here.
this game
Uh-huh.
based on if Mississippi won?
Yeah.
But if you look here, it starts out like the probability that they make it all the way. So I didn't know how to like compute their probability of winning this game based on Mississippi making it there.
So this is 89 that it goes on.
Yeah.
What about these two over here? Those things don't add up to.
Yeah, so they broke it down that
Okay.
which one won that, and then the probability that they'd win this game if they made it.
Right.
So,
Okay. So you could try and, so the chance that they would win this one, they have to win two
yeah.
in a row. Right, so the probability that, you know, they win the first and they win the second, so the probability that they win the first and the probability they win the second, given that they win the first, but the probability that they win the second is really a compound
Yeah.
thing, the probability they win the first, given that they have the, opponent A times the probability is that opponent A, plus the probability that they win the second, given that it's opponent B times the probability that it is opponent B. Right? And we can kind of, don't even need to, let's not write that in there, right? So
Okay.
from the neighboring bracket, right? So one team would come through, there's a probability of coming through, and then there's a probability of winning
Okay.
after that.
Okay.
So it looks like that they've done
Yeah. 'cause it was a
something
little
to add
confusing.
those
Yeah.
together.
Okay.
So getting at the conditional probability that they win. Right, so it gives you know this one,
Mhm.
right? You know this one, and you know this one,
Yeah.
and you know this thing, and you know this thing. Because those are the probabilities in that first level of the next, of the other block, right? So can you get, so there's two things over here. So is there a unique, I wonder if there's a unique solution. Right, so if this could be some probability, and can you make it balanced so that you get another probability over there? It seems like there's two things that you might know. So they have probability somehow, but I'm not sure exactly how they.
Okay. Yeah, we can just record that then.
Yeah. But for something complicated like that, just doing a couple steps kind of illustrate the process.
Yeah.
Okay, yeah, we'll just do it.
Yeah.
Yeah. Okay, thank you.
Sure. It's pretty neat. Looking
Yeah.
size.
Yeah.
It is, yeah.
I guess same guy does it for football and baseball too, I think, so. it's a lot.
So sometimes they do a power rating,
Yeah.
right? And then the probability one team beats the other is related to the size of the power.
Yeah, it was, because
Differences.
I was reading a little bit on how he gave the probabilities, and he looked at, like, past data about what seed beats what seed, and then broke it down even further to what the average score of each team was, and how much each seed usually beats the other seed by. So, like, first seed usually beats the 16th seed by around 20 points.
Uh-huh.
So, like, what's the probability based on, do they score a lot of 3 points and everything like that to give the probability?
So that, for the, at least for college football, they get these power ratings. And the expected difference in points is roughly the difference in their power rating. So if somebody's rating 100 and somebody's at 90, there's kind of expected 10-point difference. There's about a 3-point advantage for home field. So if the weaker team is playing at home, they would lose by on average about 7 points. And then the difference in point scores is a standard deviation about 12. The difference in scores is approximately normal. So you can take the -7 divided by the standard deviation 12 and calculate a normal probability. That's the probability of one team winning or the other, right? And so it works pretty close, but things become so unmatched sometimes in the college football. I mean, except at the kind of the tournament levels and things. Kind of just people are playing the very weak teams in their divisions, and they'll blow them out by 50 points or something, or they'll be beating them by 35 points and then put in their 4th-string team, and it won't continue to. So it kind of distorts the distribution.
Yeah, we started working with the probabilities from last year's tournament, but because Missouri beat Virginia, 16 beat
Kind of
first
threw
seed,
it off.
Yeah, threw a lot of
everything
people
off.
off.
Yeah.
So, yeah.
Well, thank you.
Yep.
I don't know if we should take a picture of that because what are the chances?
Thank you.
Thanks.